Alright, welcome back, Digital Electronics. We're on lecture 21, going through Boolean Algebra. It's got a fancy name, but it's really just a lot of basic algebra skills that you already know how to do and solve and simplify and factor and those sort of things. We just have to be able to do it with specific logic expressions that we're going through. Okay, so Boolean Algebra is very, very similar to our normal algebra that we use, but it's a mathematical technique that gives us the ability to algebraically simplify our logic expressions. So it's specific to what we are doing here in digital electronics, but yet very, very similar to our mathematical algebraic simplification. So what we've been doing is, I draw a circuit like this on the board, and we come up with the expression, and some of those expressions are going to be very long, just like your majority vote. And the majority vote, okay, is a long expression, but you're going to be able to use some of this Boolean algebra to simplify down your majority vote problem and make it much easier. So the big circuit up here can simplify down to the smaller circuit in the lower right hand corner just using some basic Boolean algebra skills. So we've got a few theorems that we gotta write down, and once again it's named after a dead math guy. Alright, this is George Boole. Alright, he lived in England in the 19th century. Did a lot of work with mathematical number systems and things like that. So that's where we got the name Boolean Algebra, after George Boole. Alright, so what I want you to do in your notes is you need to have a separate piece of paper out, and I want you to write down all the theorems. And write them out: theorem number 1, theorem number 2, theorem number 3, just like as you see above. You do not have to write the logic gates and the tables down at the bottom that you see here, but I do want you to write the theorems. Alright, so it should make sense as we go through those. The AND function. So what you need to know is x and 0 is 0. You need to know that x and 1 is x. Because it depends. If x is a 0, we get a 0 back. If x is a 1, we get a 1 back. So we need to be able to cover all of our cases here. And that's really what the tables are doing for us. So anything ANDed with 0 will give us a 0. Anything ANDed with x and 1, is going to give us an x back. Because we don't know what x is. X is kind of our unknown, but it could be a 1 or it could be a 0. So it just kind of depends on the logic value that comes through as we're doing our gates and going through. Alright, so theorem 3. X and x simplifies to x, and x bar simplifies to 0. So make sure, if you need to, pause the video, write those 4 theorems down, because we're going to add these next 4. This is for ORing. X or 0 gives you whatever x is. X or 1 is equal to 1. X or x is equal to x, and x or x bar is equal to 1. Just remember, when we're doing this, x can be a 1 or a 0. It's just going to be problem specific. Okay, and you'll see as we get through some examples it'll make sense. But I want you to have these theorems next to you, so when we apply them, you can see, oh, this is how theorem 7 applies in this particular situation. Okay, we're going to have up to like 13 theorems, and then some De Morgan's theorems and things like that we're going to add on. So your sheet's going to get fairly full of the theorems. Once again, don't write the logic gates of the tables. Just write out the theorems. Okay, so theorem number 9. If we have a double x bar, so x bar bar, okay, it equates to being just x again. So that means if we double invert x, it goes back to being x. So you send x through an inverter, it becomes x bar, and then when we send x bar through an inverter, it becomes double x bar, which in turn returns it back to being x, or being itself. That's going to come in very useful when we start doing the De Morgan's theorems in the next lecture. Alright, so let's do an example here, so we can simplify an expression down and use some of our Boolean theorems that we just learned. We just learned 9 of them. Let's see if we can apply them. So we have this first expression here: f1 equals AAB or C bar D. What I want you to think about and look at your theorems before I put the answer up here is what's going to simplify. What is A and A equal to? If you said A, that's correct. So that A and A simplifies down to a single A, so we get AB there. What is C and C bar? Well, that means, we either have 1 or 0 or 0 or 1. So one of those is going to be a 0 all the time. So C and C bar, right? One of your first 4 theorems, if you're looking at that, ends up being 0. So that whole term on the right goes to 0, and we're just left with AB. So you can guide through it like this, okay? A and A becomes A, so we're just at AB. C and C bar becomes 0, okay? So we have AB or 0 times D, or 0 and D, I shouldn't say times. 0 and D is 0. So we're left with AB or 0, which is just AB. So we should be able to simplify these down. If you might have to watch this a couple times and watch the simplification piece, but I think you'll be able to get these down. Let's do another example here. We have F2, which is B and C bar, or B and C bar, or A bar, B and 1, or A bar or A, B bar, 0. Let's mentally process one together. Moving left to right, we have B and C bar. How can you simplify that one down? Well, B and B becomes just B. So that one simplifies down to B and C bar. Let's look at the next term. We have B, C bar, C bar. What is C bar and C bar? It's just C bar. Anything ANDed with itself is just itself. So that term can become B, C bar. The next term we have A bar, B, and 1. Well, all that stuff is ANDed with 1, so it really just becomes A bar, B. Then, on the last term, we have A, B bar, 0. Well, it's ANDed with 0. Anything ANDed with 0 becomes 0, so that last term goes away. Okay? So then we can even maybe potentially simplify down more. We'll have to check it out as we go through these. But they should all simplify down, all right? So the B, C bar, B, C bar, now there's 2 of those, right? There's a B, C bar or a B, C bar. If there's 2 of those, anything ORed with itself is just itself. So we can eliminate that, all right? So where it says theorem number 3 twice, that's really what we're doing, okay? You have B, C bar or B, C bar. Those become, since they're ORed, they become just B, C bar, okay? And we walked through the other ones. So the final answer here is just B, C bar or A bar, B. All right, let's write down a couple more theorems. You might recognize the verbiage from math class, the commutative law, right? Meaning what? Order doesn't matter, essentially. So we can say X and Y or Y and X. So that's the commutative law for the AND function. Then we have the commutative law for the OR function. So that's why it's 10a and 10b. X or Y is the same thing as saying Y or X. And if you ever get confused on any of the Boolean stuff, just replace, everything with 1s and 0s. If there's no bar over it, it gets a 1. If there's a bar over it, it gets a 0. And just see how it works out. All right, let's look at the associative law. So once again, there's 2 of these, one for the AND and one for the OR. You're going to get X and the quantity Y and Z is the same thing as X and Y quantity Z. And you can see for the OR, I don't need to read it off. You guys can go ahead and write those down. So make sure that you have those theorems. This one's an important one, and you should know this from math class. The distribution law, okay, that's number 12a here. When we have anything outside the parentheses, it can distribute into the parentheses. So we have that X has to distribute to the Y and to the Z. So we end up getting X and Y or X and Z. In the bottom one, that's just FOIL, binomial multiplication, or the box method, however you learned it. First, outside, inside, last, whatever you need to do. You're going to multiply those. So X is going to get multiplied by W, and X is going to get multiplied by Z. y is going to get multiplied by w and y is going to get multiplied by z. So however you need to expand that out, okay? That's the distribution laws there. Alright, so let's apply the new laws that we just learned. So we're going to work through example number 3 here. We have the Boolean expression f subscript 3 is equal to r bar t or r or s bar or r bar or t. Now, what you should be asking yourself, how do I approach this problem? Well, the first thing I would do is multiply the r or s bar and the r bar or t. I would FOIL that out. Alright, and then see what that gets you from there. Look for where you have r and r or r and r bar or different combinations of things like that might happen. So here's everything laid out step by step. So when we FOIL all that out, you're going to get the step 3 down there, r bar t or r bar or rt or s bar r bar or s bar t. I'm reading the very first thing next to theorem 12b. So now we got to simplify some things down. We can see that the r and r bar can become 0, okay, using one of the first 4 theorems we learned. Then the next step, what else can we see that we can simplify down? Start combining things closer together or rewrite them. Next, it's calling out for theorem 12a. Okay, right there, if you look at the line next to theorem 5, okay, we have 3 different terms that have a t in it. The r bar, the r, and the s bar all have a t. So I can factor a t out of those 3. When I factor a t out of those 3, I'm left with an r bar or r or s bar, and then that's all ORed with s bar r bar. So what did I do that for? Well, you have to recognize that r or r bar becomes 1. Alright, so this is having your theorems out and next to you. So r or r bar becomes 1. So that leaves us with t times the quantity of 1 plus s bar or s bar r bar. Okay, t can distribute to the what? 1, right? Think about this part. Why can that just become 1? Because we have 1 or, in your theorem it's 1 or x, but in this case we have 1 or s bar. 1 or anything is always a 1. Okay, so that leaves us with t and 1 or s bar r bar, which simplifies us to t or s bar r bar. So you got to look for those different things. That's why it's really important that you have all these theorems kind of on a sheet next to you, all nice and neatly organized when you work through your homework problems. Alright, so let's look at the last theorem here before we get to the De Morgan's. Alright, we're going to look at the consensus theorem. This is probably the hardest one to remember. Okay, so this is why it's good for you guys to write this down. So we have 4 versions of it. Okay, really it's just kind of we're playing where the bars go and what the output's going to be. So if we look at 13a, we have x or x bar and y. That can simply reduce to x or y. It's a very simple reduction there. Let's look at b. Alright, we have x bar or x and y. That reduces to x bar or y. Because essentially the value next to the y in part A and B is obsolete because of the leading value at the front. Okay, so that's what's really going to go on there. So it'll always be the other variable with whatever's leading in front of the or. So let's look at C. We have x or x bar y bar. That is equal to x or y bar. Okay, so just once again, whatever's next to whatever the 2 term is goes away. And then part D, x bar or x y bar equals x bar or y bar. So you can kind of see which one's being eliminated when we do the consensus theorem. So let's do a Boolean expression that involves a consensus theorem. Okay, so make sure that you guys write all these down. So we have F4 equals PS or P not Q not S or PQS. Doesn't look like we have a lot of simplifying going on within itself, right? There's not a letter next to itself or next to its bar or things like that. What we can see is maybe some different things that we can factor out. I can factor a p out of all these terms. Okay, that might help me. That's very common. I can group them and factor a ps out of one of them, right? The first term and the last term. And I can factor out, if I factor out the ps, I get 1rq and the q goes away and I'm left with a ps. Alright, so there's different aspects of things. There's multiple ways to solve these problems, okay? So make sure that you understand how you're going to factor and what your approach is going to be. So like I said, there's a couple different ways to approach this. You just got to get comfortable. You'll all end up with the same answer, okay? Alright, let's take a look at the solution. So if we factor the p out, like I was talking about, alright, we're left with s or q bar s bar. Notice that what goes on right there, that gives us an automatic consensus theorem. We have s or q bar s. We can rewrite that as s or q bar. So there we can apply the consensus theorem. Then we would want to distribute back through in this case. We're going to distribute the p through to the s or q bar. So you're going to get ps or p not q or pqs. Now we can factor out, like I was saying earlier, factor out the ps from the first term and the last term. Okay, we're going to leave the middle term alone. So when we pull a ps out, we get a 1 or a q or p not q. The 1 or q becomes what? 1. So we're left with a ps or pq bar. There's really nothing else we can do. We could factor a p out of that, alright, and be left with s or q bar, but s or q bar doesn't necessarily simplify down using any of our theorems. We'd have to know the exact values for s or q bar. Alright, but the final answer here is ps or pq bar. Alright, so remember there's multiple ways to kind of get to that answer, but you will get to the same answer. Alright, so just in summary here, this is everything that you should have on your cheat sheet or your notes. This is all of the Boolean theorems that we have laid out. So if you need to pause the video and write them down. But if you have them all in one location, it's really going to help you when you work on the assignment. Alright, well that's it for this lecture, guys. So please either email me with questions or ask questions in class. We can do some more sample problems or things like that. Alright, else guys, have a great day and I will talk to you soon.